radians. Now I'm going to think in degrees, but I'll change it over to radians. And I know that 2 pi radians is 360 degrees. I need a convenient way to go from radians to degrees, and there's a formula that you'll either have to be looking up continuously, or you'll have to memorize or learn to figure out. I know that 2 pi radians is 360 degrees. That means that pi radians is 180 degrees, and it follows that 1 radian is 180 degrees divided by pi. So if you would like to go from radians to degrees or degrees to radians, use this equivalency, and it's a nice and easy way to get it. The next little bit talks about the fact that we get our trig functions from the unit circle, and this unit circle is of radius 1, and I can make any of these triangles from this unit circle. So they're basically showing you how to make the right triangles and what the relationship of sine and cosine in those right triangles in relationship to a circle is. Now the unit circle has a radius of 1, but these relationships hold for if I'm going to look at the unit circle, and I went ahead and snipped a unit circle from embeddedmath.com so that I can see both the degrees and the radian measure on there. They've asked me to evaluate the trig function for sine of 8 pi over 3. 8 pi over 3 is basically, here's 1 pi over 3, 2 pi over 3, 3 pi over 3, which reduces to pi, 4 pi over 3, 5 pi over 3, here's 6 pi over 3, which is 2 pi. That would make this 7 pi over 3, and then 8 pi over 3. So this is the same thing, or I get the same result as 8 pi over 3 by just keeping on going around the circle. The sine value, those are the y's. So here's my point, and I'm going to choose the y point. Square root 3 over 2 would be the exact value for this. You're going to want to play with exact values rather than approximate values that you get off your calculator. When I've changed it to a decimal and rounded, I am doing approximate values. Cosecant is 1 over sine of that negative 11 pi over 3. So the negative just tells me to go around the circle. 3, negative 5 pi over 3, negative 6 pi over 3, negative 7, negative 8, negative 9, negative 10, negative 11. Here would be negative 11 pi over 3. Sines are the y values, and that would be 1 over square root of 3 over 2. Means I would flip this, 2 over square root of 3. Some mathematicians might have a fit over this, so they would want you to rationalize this denominator. And how you would rationalize that denominator would look something like square root of 3 times square root of 3 is square root of 9, and that's what it would look like rationalized. Here are the various trig identities that you're expected to kind of have memorized and or be very familiar with, know off the top of your head, I guess. So if I'm solving this trig equation here, I'm going to move the 1 over it and then divide by the square root of 2. So it would look something like this. I'd like to look over here and see one of those values, but I don't see it. But I have that square root of 2 in the denominator, so let me rationalize it, see if there's something over there matches it. Negative square root of 2 all over, this would be the square root of 4, so that would be a 2. Oh, I see something that matches it. I have a winner. Let's see, sine are the y values, so I need to go down here. Here's a winner, and there's a winner. So I actually have two answers here for x. X can be equal to 5 pi over 4, or x can be equal to 7 pi over 4. But that's not the only thing it could be, because what if I went around the circle again and say I added 8 pi over 4 to that, just adding 2 pi, meaning go around the circle again, so that 13 pi over 4 would be a solution to this as well. And I could go around the circle again, and I could go around the circle backwards. So in order to get that entire family of solutions, I'm going to say that I'm going to add 2n pi, where n can be any integer. I wonder if 0 works. Does 0 work? Oh yeah, because then that's just 5 pi over 4, so that works too. So plus minus 1, plus minus 2. So really n is any integer. You could also write that, if you want to write it in notation, you can say n is an element of the integers, and that double-lined z represents its symbolism for the set of all integers. And the same goes for this bad boy right here. Alright, move some stuff around. Looking at the b part, I've got a sine and a cosine there, and I don't like either one of those things. It's handy that they have restricted my domain so I don't have to do this family of solutions like I did on the a part. That's nice. I don't like having a sine and cosine, so one of the tricks of the trade is to go ahead and make it into another form, like a tangent or a cotangent. Personally, I like tangent better, so I'm going to divide both sides here by cosine 2x. Cosine 2x. I will get tangent 2x equal to 1. I'm a lot happier with that right there. I'm going to put in place a dummy variable here because I'm not really sure about this 2x. So if I just put in this dummy theta equal to 2x, this will be easier on the eyes. Tangent theta equal 1. Now tangent theta is going to equal 1 right here, because square root of 2 over 2 divided by square root of 2 over 2 is 1. Also on this side as well. So does that fall in 0 to 2 pi? Yep. Will this one work? No, this one won't work because that would be a negative 1. This one won't work either because that would be a negative 1. My theta here is either going to equal pi over 4 or 5 pi over 4. But that's not really what I'm looking for, because I'm looking for what x is. And I know that 2x is what theta is, and that would equal pi over 4, or 2x equals 5 pi over 4. So for this case, x equals pi over 8. For this case, x equals 5 pi over 8. But that's not my only set of solutions, because I had this domain restriction here and I didn't consider that when I looked at this. So if x is in between 0 and 2 pi, that means 0, 2 theta over 2 is in between 0 and 2 pi, because x is theta over 2. Our theta values, because we changed this domain somewhat, I'm going to multiply everything through by a 2, can go from 0 to 4 pi. So I have to consider this extra where I was able to add in another round, if you will. This pi over 4 here, going that other round, plus 2 pi would be, do this one out to the side, 2x equals, add 8 pi over 4, so that would be 9 pi over 4. Solving that, I would get 9 pi over 8. This guy here going another round would be 2x equals, add that 8 pi over 4, it would be 13 pi over 4, giving me, dividing both sides by 2, 13 pi over 8. So because of that 2x in that tangent, what happens is it's going to double my number of answers, or it could possibly double my number of answers. As a quick review to graphs of functions, you'll need to know how to find the period of sine, cosine, secant, and cosecant are both 2 pi, and the period of tangent and cotangent are pi. Here are the graphs of each. Here's the graph of sine in red, and if I take those y values and take the reciprocal, because that's what cosecant is, here you'll see in blue those reciprocal values. Every time the sine was 0, 1 over 0 is undefined. That's why you have this huge vertical asymptote happening on all of those cases. Now your textbook has a nice little interactive graph that we should look at. On this interactive graph, you can just click you're sitting here looking at a sine function, you can click the little graph and get the cosecant. I'm looking at the graph of a cosine function. Click, and I'll get my secant and my cotangent. Now, graphing of trig functions is an entire chapter in a textbook. If you're needing some review on that, once again, be sure and let me know, and we can set up a collaborate to do that review. Now this little grapher is really worth his weight. The other one wasn't really much of an interactive, but I still got to play with it anyway. This one is worth his weight in gold here. Of course, I don't know how much he weighs. The D is my vertical shift. It is adding on the outside. So I'd like to look at what D does when I increase. It raises it. Looks like a little piece of wire, doesn't it? Just increases it, and as D goes down, or as D is negative, it decreases it. Perfect. Now let's look at what that C does, because the C is adding and subtracting on the inside, and we've looked at this before. What it did before was a horizontal shift, moved it left and right. Let's see what happens now. Oh yeah, it's moving it left and right, kind of making me dizzy there. Okay, that's C. The A is actually my next favorite, so I'll play with him next. The A, and this is so perfect because it shows this vertical and this horizontal stretch and shrink as no other function can really do. This A as I increase it, shows that vertical stretch. As I decrease it, shows that vertical shrink beautifully. Due to the symmetry of some of our other functions and the way that they're laid out with the x and the y correspondence, we don't get to see this horizontal stretch and shrink. But with this particular function, it is so awesome. I love this function. So as I increase b, look at the horizontal. See, it shrinks up, and as I decrease b, notice that it is stretching out. And as b is negative, it actually flips. Alright, so this is modulating the frequency, as we would call it in electronics or physics. A beautiful way to show the transformation of graphs. You might want to play with that just to get a good feel for what's going on. Now that we've looked at these graphs, notice that the sine function and the cosine and the cosecant and the secant and the tangent and the none of these guys are one-to-one. Absolutely none of them. In fact, they're just so far removed from one-to-one because they continue on and on repeating themselves. So we either say that they don't have an inverse, or we can restrict the domain, which, by the way, is what we do. They've got a little interactive graph where they kind of erased the sine function, and they show that what they did for the sine is they restricted the domain from negative pi over 2 to positive pi over 2. They could have chosen from pi over 2 to 3 pi over 2. They could have chosen from this section, this negative pi over 2 to the negative 3. They could have chosen anywhere to restrict the domain to, but they chose somewhat in the center, it being centrally located. When you do an inverse sine, you have to remember that the domain has been restricted to in between pi over 2 and negative pi over 2. So if you have an answer for an inverse sine that is outside of this realm, then it is incorrect. For the cosine of x, it would have been nice if we could have chosen the same domain from negative pi over 2 to pi over 2, but we couldn't because that's not one-to-one in that particular set of values there, in that range of values. They chose from 0 to pi to restrict the domain of cosine, and anytime you're dealing with the inverse cosine, you'll be dealing with that particular set of values. We'll work a few problems, and I wrote up at the top how our domain was restricted. I want the inverse sine of square root of 3 over 2, so I'll go and find some square root of 3 over 2's. There's one. Ooh, and here's one. Here they are. The domain has been restricted to the negative pi over 2 to positive pi over 2. So I have to pick which one would work for that domain restriction in between negative pi over 2, that would be here, to positive pi over 2. Which answer would work for this? Because we can only have one if it's to be a true inverse function, and it looks like it happens to be pi over 3. I will play the same game again for this b. Do it in a different color. Negative square root of 3 over 2. Now cosine are the x values. So I go to the x values, and that would be this guy here, or this guy here. Cosine is valid in between 0, and pi. That's where I restricted the domain. So the answer for this guy, pi over 6. Our C question is a little bit tricky, so let's look at it closely. The domain of the cosine has been restricted, so the answer to this can't be 3 pi, because that wouldn't fit with our domain restriction. But I do have an answer for the cosine of 3 pi. Let's see, that would be, there's 1 pi, 2 pi, 3 pi. The answer for cosine here is -1. And the inverse cosine of -1 has a cool answer. It's pi. The D question. So it pays to make sure, because you know your first instinctive response is to want to say, well, that answer is 3 pi, but that answer is not 3 pi. It is pi due to the domain restrictions. Whoops. Alright, let's play our game. I need the y value within this red of 1/2. There he is. Pi over 6. And now I need the sine of pi over 6. Oh, this one is 1/2. We're going to use right triangles to solve this. I know that sine of theta is opposite over hypotenuse. So I'm going to draw a triangle. Ooh, it's pretty good. There's going to be theta. The opposite of this is a 2. The hypotenuse there is a 5. I can get this other value by using the Pythagorean theorem. A squared plus b squared equals c squared. So 2 squared plus b squared equals 5 squared. B squared equals 25 minus 4 is 21. B is then going to be the square root of 21, whatever that might be. They want me to find cosine theta and the tangent theta. Tangent is adjacent over hypotenuse. Tangent is opposite over adjacent. So let me just plop those down. Adjacent to this theta is square root of 21, hypotenuse 5. Opposite is 2, adjacent is square root 21. I'm going to play it again. This time they want me to write this whole thing in terms of x, and I'm going to use a triangle again. Cosine is adjacent over hypotenuse. So I'm going to, in order to get this side, once again, I'm going to use the Pythagorean theorem. I'll just call this b for right now. X squared plus b squared equals 4 squared. B squared equals 16 minus x squared. B is equal to square root 16 minus x squared. So this b is then square root 16 minus x squared. Alright, I need cotangent of cosine. There's 1, x over 4. And I built this theta. I built this theta right here using the right triangle. So I know that cotangent is, if tangent is opposite over adjacent, it would be adjacent over opposite. So this would be adjacent, that is x over the opposite square root, 16 minus x squared. Keeping those unit circles. You want to keep one of these unit circles handy whenever you're working with these. I'm looking for, tangent is sine over cosine. I'm looking for something. It's going to be in one of these two quadrants so that I can have a negative value. And I want sine over cosine. I want the square root of 3 to end up in the denominator, so I want either this guy or, let's see, this one, because 1/2 over that would make the square root of 3 in the denominator. Cool. My domain, so either one of those two, my domain says choose the value that's in between negative pi over 2 and pi over 2. That would be somewhere in between here. So apparently I'm going to pick 11 pi over 6. Oh, but I can't write 11 pi over 6, can I? I have to write it so that it's in between there. Let's write it as negative pi over 6, because secant is 1 over that cosine answer. Cosine is its domain from 0 to pi, so I choose the x value that is negative 1/2. There he is. That would be this guy here, and that will be 2 pi over 3. Next, I'm going to look at the sine of the tangent. Okay, so I'm going to build this theta using a right triangle. It's my favorite way to do it. X, it can be written as x over 1, and tangent is opposite over adjacent. So here's my theta. Opposite is x, adjacent is 1. Following the Pythagorean theorem, a squared plus b squared equals c squared. Bx squared plus 1 squared equals c squared. Means this guy right here is going to be x squared plus 1. And sine of that theta is opposite over hypotenuse, so sine tangent minus 1 x would be equal to opposite x over square root of x squared plus 1. And believe it or not, we'll be using these triangles later on in the course.